You ever look at a statistic or a study and just get a feeling that you're not seeing the whole picture? Well, today, we're putting on our detective hats. We're going to dig into how researchers find the real story behind the data using a powerful tool called experimental design. And our first case is about a cookie.
So, picture this, a simple taste test. People who try a new chocolate chip cookie absolutely love it. The folks who try a raisin cookie, not so much. The conclusion seems pretty obvious, right? Chocolate chip wins. But what if I told you there's a hidden clue in this experiment? A secret ingredient that could change everything we think we know?
Okay, here's the case file. The cookie type, that's our independent variable. It's the thing the researcher is changing on purpose. The rating people give it, that's our dependent variable. It's what we're measuring. And yeah, the chocolate chip cookie got a 6 out of 7, while the raisin only got a 3. Case closed, right? Well, not so fast. Look at that line at the bottom, the hidden culprit. Turns out, the chocolate chip test happened at 11 a.m., right when everyone's getting hungry for lunch. The raisin test? That was at 1 p.m., after most people had already eaten. So, was it really about the cookie, or was it about hunger?
That hidden culprit has an official name. It's called an extraneous variable, or a confound. And you should think of it as the villain of our detective story. It's this sneaky outside factor that messes with our results. It creates what's called a spurious association, a connection that looks totally real, but it's a fake. The entire goal of good experimental design is to hunt down and get rid of these villains.
So, how do we build a case that's actually airtight? How do we get to a point where we can confidently say that one thing truly causes another? Well, it turns out there's a strict code, a set of rules that every good researcher and every good detective has to follow.
But first, a really important reality check. In the real world of research, you can never say you've proven a cause with 100% certainty. It's just not how it works. Instead, your job is to gather so much compelling evidence that any other explanation just seems, well, unbelievable. You're not so much proving a case as you are building an overwhelmingly strong one.
And here are the 3 golden rules for building that case. Rule number 1, the cause has to happen before the effect. Makes sense, right? Rule 2, they have to vary together. You know, when we change the cookie, the ratings also have to change. And rule 3, and this is the big one, the hardest one of all, we have to eliminate all other possible causes. We have to get rid of all those pesky extraneous variables.
Okay, so if getting rid of those hidden culprits is the key to the whole thing, what tools do our research detectives actually have to do it? Let's open up the toolkit and see how they control their experiments to catch these villains in the act. The most basic, fundamental tool in the entire kit is the control group. The experimental group gets the thing we're testing. They taste the new cookie. But the control group, they get nothing. They act as our baseline. They show us what would have happened anyway, which lets us isolate the true impact of our cookie. And now for the hero of our story, random assignment. This is, without a doubt, the single most powerful tool a researcher has. Here's how it works. You assign people to the experimental group or the control group completely by chance, like flipping a coin. Now, this doesn't magically get rid of extraneous variables like hunger or age, but it ensures they're spread out evenly across both groups. It stops them from ganging up on one side and biasing our results. It's a total game changer.
Now, there are other cool tools in the kit too. You can use blocking, where you group similar people together first, say by age, then randomize them. You can use repeated measures, where every single person tries both cookies, but if you do that, you've got to use counterbalancing, making sure half the people try cookie A then B, and the other half try B then A, so the order doesn't mess things up.
Now, every single investigator, every researcher faces this really tough choice. It's a fundamental dilemma. Do you run your experiment in a super-controlled, sterile lab, or do you take it out into the messy, chaotic, unpredictable real world? And this choice really comes down to a trade-off between 2 things. Internal validity is all about control. It's your confidence that your independent variable, your cookie, really caused the change you saw. Think of it as a clean, perfect interrogation room. On the other hand, you've got external validity. That's about realism. It's your confidence that what you found in your experiment will actually hold up out in the real world. And this quote from the source material just sums it up perfectly. A lab experiment gives you tons of control, which means you have high internal validity. But the results might be a little artificial. A field experiment, out in the wild, is super realistic, giving you high external validity. But it's way, way harder to control for all those hidden culprits.
A fantastic real-world example of this whole dilemma is the blind experiment. You might remember this. Back in the 80s, Coca-Cola ran these huge blind taste tests. People didn't know if they were drinking old Coke or a new formula. The results were crystal clear. People preferred the new stuff, high internal validity, right? But when they actually launched new Coke, it was a legendary disaster. And why? Because in the real world, people don't just buy a taste, they buy a brand. The blind test had low external validity because it totally ignored the one thing that actually drove people's choices.
So how do researchers put all these tools together and deal with these tricky trade-offs? Well, they use established blueprints, or what we call experimental designs. And some of these blueprints are just fundamentally flawed, while others can help you build an almost airtight case. Let's look at the evidence.
Basically, all designs fall into two major categories. You've got quasi-experimental designs, which are missing our hero. They don't have random assignment. Because of that, they can't fully control for those hidden culprits, and they have weaker internal validity. Then you have true experimental designs. They always use random assignment, which gives them much stronger internal validity.
Let's open a case file on a super common but flawed quasi-experimental design. It's called the static group design. It's pretty simple. You just compare a group that got a treatment, say they saw a TV ad, to a group that didn't. The flaw seems obvious now, right? The groups might have been totally different kinds of people to begin with.
And check out this real-world example. A company called Sharpcraft Bass Boats aired an ad on a hunting and fishing show. Afterwards, they called a bunch of people. Get this. Of the people who saw the show, a whopping 84% knew about the brand. Of those who didn't see it, only 1% knew about it. I mean, wow, right? That ad looks like a massive home run.
But hold on, let's play detective. Was it really the ad that caused that huge difference? Or is it just that the two groups were fundamentally different from the get-go? I mean, people who choose to watch a hunting and fishing show are probably already interested in things like bass boats. They're more likely to know the brands with or without the ad. That is a classic textbook extraneous variable.
So how do we fix it? We bring in a true experimental design. This one is called the post-test only with control group. It looks almost exactly the same as the last one, but it has one tiny game-changing addition. We randomly assign people to either see the ad or not. That simple act of randomization makes it almost certain that the two groups are comparable from the start. Now we can finally isolate the ad's true effect.
So here it is, the bottom line. If you only remember one thing from this whole explainer, make it this. Random assignment is the detective's absolute best friend. It is the single most powerful weapon a researcher has for neutralizing those hidden culprits and building a truly convincing case for cause and effect.
So, to wrap everything up, here's your very own detective's checklist for the next time you see a headline about a new study. First, always ask yourself, what could be the hidden culprit here? What's the confound? Second, quickly run through those 3 rules of causality. Third, look for the hero of the story. Did they use random assignment? And finally, think about that trade-off. Was this a controlled lab experiment, or was it out in the messy real world? Because now, you have the toolkit. You know the rules of the game, and you know how to spot a flimsy case. So the next time you see a headline that boldly claims A causes B, you'll be able to look a little closer, ask the right questions, and maybe, just maybe, you'll be the one to spot the real story.